First, write down all of the positive whole numbers in the world. Then, take away all the numbers that are multiples of 2. Then, take away all the multiples of 3. Then, take away the multiples of 4 and 5 and 6 and so on. The numbers that are left are the prime numbers. Prime numbers are all of the integers that have no factors other than 1 and themselves. And no, 1 isn't considered a prime number itself. Now, you might be thinking that prime numbers don't seem particularly special. However, numerous special properties of prime numbers have been discovered over many years that have made them very desirable. Let's take a look at how.
Firstly, it should be noted that all non-primes are products of 2 or more prime numbers. Of course, this must be the case by definition. If a number is non-prime, then it must have factors. These factors are either prime themselves or not prime, those of which we can keep cutting down until we only have prime numbers at certain powers multiplying each other to represent a non-prime number. Prime factorization is the process of breaking down a number into prime numbers that are factors of that number. For example, if we want the prime factorization of 72, we can find that 72 equals 9 times 8, which equals 3 times 3 times 2 times 2 times 2, or 3 squared times 2 cubed. And if we choose 31, which is a prime number, it would only have one prime factor, being 31. 1 is not considered to be another prime factor, as 1 is not considered to be a prime number in the first place. Following? If not, our next topic, visualizations of prime numbers, might be able to help.
Hold up.
When it comes to understanding a concept, it can be helpful to find a way to visualize it. There have been many attempts at creating visual representations of prime numbers in the past. Let's take a look at a couple before we continue. To start off, we found a pretty cool online visualization of prime factorization that creates subdivisions of numbers based on their prime factors. If the current number itself is prime, then it forms a circle, since you can't make any subdivisions. If we look at our previous example of 72 on this, we see that there are 3 main subdivisions, and inside of them, 3 more subdivisions. Inside of those, 2 subdivisions, and inside of those, 2 more subdivisions, and then finally, 2 more subdivisions. This whole image represents the prime factorization of 72. 3 times 3 times 2 times 2 times 2. Next up, we'd like to show you a couple spirals, all of which adhere to the same idea in that you start at the middle at 1, expand outwards to 2, then to 3, and so on, then highlighting all of the primes. There are a couple named spirals that follow this rule, such as the Ulam Spiral and the Sachs Spiral.
The Ulam Spiral creates a square pattern, and you can find some distinct lines and patterns within it. Formulas for finding primes create shapes or lines when the results are marked on the Ulam Spiral. You can find one of such shapes by highlighting specifically primes of the form 4x squared minus 2x plus 41, starting at x equals 0, which eventually forms a straight line. The Sachs spiral is very similar to the Ulam spiral in how it is drawn. However, the trick to making it is by aligning all perfect squares on the east side. For example, moving once to the right from the center at 1 will find you the number 4, and doing that again will land you on the number 9. Formulas for finding prime numbers also create strange patterns on the Sachs spiral. However, they create smooth curves that move towards its west side, making them much easier to visualize. Here's a picture showing formulas for finding primes and their curves created when highlighted on the Sachs spiral.
Big chungus, big chungus, big chungus, big chungus.
Now for some quick, less important facts. Did you know that all natural numbers are a product of prime numbers as well? This is very similar to prime factorization.
As prime numbers become larger and get more and more digits, they become less and less useful. That doesn't mean they will ever become useless, it's just that their real-life applications do become obsolete. For example, they become too large for computers to process for use in things like encryption.
A species of cicadas named periodical cicadas stay underground for 13 or 17 years, which are prime numbers, before resurfacing to mate and lay eggs. Most predators of cicadas have 5-year cycles in their population, and given that cicadas come out every 17 years, their appearances normally wouldn't coincide with their predators. It would take 85 years for these cycles to meet, so I guess cicadas are pretty darn smart.
Contact gears will usually have a relatively prime number of teeth. 16 and 25 would be relatively prime since they share no factors. This will more evenly distribute the wear, as it will make it so the same teeth do not always press against each other while the gears are turning.
The Great Internet Mersenne prime search has a really cool ring to it. We'll go over this more later, but in short, Mersenne primes are any prime of form 2 to the n minus 1, or n is a known prime number. The website mersenne.org likes to abbreviate its name to GIMPS, and it was founded all the way back in 1996 by George Woltman. Since then, GIMPS has discovered 17 Mersenne primes. How are they finding these primes? People volunteer through the website to use their computer's processing unit to contribute to the search.
This is a certified hood classic.
Here's a lesson in trickery. This is going down in history. If you wanna be a villain, number one.
Circa 350 BC, Greek mathematician Euclid was able to prove the existence of an infinite number of prime numbers by contradiction. His modernized proof is as follows. Assume that there exists a finite number n of primes, the largest being p sub n. Consider a number, big N, that is a product of all primes p sub 1 to p sub n plus 1. By construction, big N is not divisible by any p sub x. Hence, big N must either be a prime itself or have a prime factor that's larger than p sub n, showing that there's a larger prime regardless of the outcome. An example of this would be if you used n equals 4. Big N would equal 2 times 3 times 5 times 7 plus 1, since 2, 3, 5, and 7 are the first 4 primes. Simplified, big N would be 211, which is a confirmed prime number. The proof is modernized because Euclid made this proof before the time of algebra. When he proved this, he actually used line segments to represent the size of a number rather than variables, and he defined prime numbers to be the line segments that couldn't be evenly broken up into other lengths of line segments.
You have to chase a superhero on the run.
Assume the density of primes represents the percentage of numbers that are prime below a given bound. As x equals size increases, we can find that the y equals density of primes decreases. However, this relationship isn't linear, and the prime density never reaches 0. In fact, it seems as if it's an inversely logarithmic function, such as 1 over log of x. The estimation is pretty close, and the prime density y is actually approximately equal to 1 over the natural log of the current size x. This formula becomes more and more accurate as x increases, so as x approaches infinity, the difference in percentage of the estimate and the percentage of the actual number of primes under x approaches 0.
And in red is the plot of prime number density up to x. As we zoom out, they approach each other. The further we zoom out, the more accurate the green estimate becomes.
We can actually now find the number of primes up to x. Using the formula to find the prime density, if we just multiply our answer by the size x, we get x over ln x as our approximation. This is the prime number theorem. Similarly to the prime density calculation, as x reaches infinity, the difference between our estimate and the true number of primes under x approaches 0. For example, if we compare the actual number of primes beneath 100 trillion to our estimate, it shows that we are 96.9% accurate, even at a relatively small scale when talking about primes. The prime number theorem was first introduced as a conjecture in 1798 by French mathematician Legendre, later proved in 1896 by Hadamard and this person, when they showed the limit as x approaches infinity of x over ln x equals the true number of primes under x.
Another notable theorem is Bertrand's postulate. Bertrand's postulate states that for any integer n larger than 1, there will always be a prime number larger than n but less than 2n. This was proved in 1852 by Pafnuty Chebyshev. Their methods are far beyond our knowledge, and we will not be covering it, although if you are interested in the proof, you can check it out for yourself.
Despite how much time and effort has been put into researching the properties of prime numbers, there are still many conjectures about prime numbers that have yet to be solved. Here's a quick list of some of the current notable unanswered questions of prime numbers. Also, before we get into it, we go over a few conjectures in this part. And so you don't get lost, a conjecture is essentially a proposed idea, sort of in the form of a question. It is unproven, but still may work in certain scenarios. The twin primes conjecture is a weird one. It asks if there are infinitely many twin primes. A twin prime is where there exists a prime and then another prime that differs by 2 of the original. For example, 1719 is a twin prime, along with 4143. This conjecture was originally stated in 1846 by Alphonse de Polignac, who wrote that any even number can be infinitely expressed as a difference between 2 consecutive primes. When the even number is 2, it represents the twin primes conjecture. 2 equals 5 minus 3 equals 19 minus 7 equals 43 minus 41, etc. Little progress was made on this until 1919, when Vigo Brun showed that the sum of the reciprocals of all of the infinitely many twin primes converges to a constant, currently known as Brun's constant. This constant, after using the twin primes up to 2 times 10 to the 16, has been approximated to be 1.9021605, and then it just goes on, and could be used to help progress the Riemann hypothesis, which is one of the Millennium Problems. The Millennium Problems are some math problems proposed in 2000 by the Clay Mathematics Institute, and if someone solves one of them, they are granted $1 million from the institute.
Conjectured in 1742, Goldbach's conjecture is one of the oldest and best-known unsolved problems in number theory. It states that every even number greater than 2 can be written as a sum of 2 prime numbers. This has been confirmed to hold true for all even integers up to 4 times 10 to the 18th. Despite that, it remains unproven for almost 3 centuries. Why only even integers? Well, that's because all primes other than 2 are odd, and 2 odd numbers added together will always get you an even number. There is actually a way to estimate how many ways we can add 2 prime numbers together to get a certain even number. We use the formula 2m equals p plus q, 2m so m becomes even, and p and q must be primes. By definition, one of the primes must be larger than or equal to m, and the other must be smaller than or equal to m. The chance that any number you choose between m and 2m would be prime is 1 over ln m by the prime number theorem. If we were to change p and q to just a and b, and not necessarily assume that they are primes anymore, the chance that a is prime would be 1 over ln m, and the same applies to b. If they are independent, the chance that they would both be prime would be 1 over ln m squared. Since a can be any number between m and 2m, there will be m choices for a, so now we can multiply our previous equation by m to get m over ln m squared to be the possible number of ways to write 2m as the sum of 2 primes.
Legendre's conjecture, which is among many attempts to estimate the gaps between prime numbers, states that for every positive integer in n, there is a prime number between n squared and n plus 1 squared. Since its proposal, it has neither been proved nor disproved. If it is true, then the gap between the current prime number p1 and the next prime number p2 would be at most the square root of p1. This same gap length is relevant to several other conjectures too. Could there be an equation that can be used to find all prime numbers? So far, no such equation has been created, but many people have stepped up to the challenge and made formulas that can at least predict some primes.
Euler's lucky numbers are numbers that when plugged into a certain equation will cause the equation to always give a prime number. Only 7 of these numbers exist, and they are 1, 2, 3, 5, 11, 17, and 41. The aforementioned equation for these numbers is k squared minus k plus n, where n is the lucky number, and k is some number between 1 and n minus 1 inclusive. This means that we can't use any k value outside of 1 to 10 if we use n equals 11. If we use n equals 41, the largest of Euler's lucky numbers, the equation nets us these numbers, all of which are prime.
Mersenne primes, like we said earlier, are a form 2 to the n minus 1, where n must be a known prime number. Notice how in this picture, only 2 squared, 2 cubed, 2 to the 5th and 2 to the 7th are prime numbers. That's because 2, 3, 5, and 7 are primes. The Mersenne formula finds both primes and non-primes, so to make this distinction is very important.
This series adds together the factorials of n to 1 alternating so that n factorial is always positive. Starting with n equals 3, when we simplify, our answer will be 5, which is prime. Doing that again with n equals 4, we would get 19, which is also prime. From n equals 3 to n equals 8, this series is successfully able to find primes. However, like most methods of estimating primes, it eventually fails. Once we reach n equals 9, our answer ends up being factorable.
Mills constant is a number that you can raise to 3 to the n and round down, and for every value of n, you will find a prime number. It is typically referred to with a theta symbol, and its approximate value is 1.306377.8, and it goes on and on. When n equals 1, we get Mills constant cubed, and once we get that, we round down, ending up with 2. When n equals 2, 3 squared equals 9, so Mills constant to the power of 9, and rounded down, we get 11. When n equals 3, 3 cubed equals 27, and if we plug that in, we get 1361 as our answer, which of course is also prime. When n equals 4, we plug everything in and get 252,100,887, and that is also prime. This formula absolutely works. However, the scale of the primes that we find gets out of hand very quickly. When using higher values of n, the computers struggle with finding the answer since it's so large. But what is more important is that you need to know Mills constant to an enormous degree of accuracy. This is still worthy of mention though, since it shows that Euler's lucky numbers aren't the only way to find primes with a 100% success rate.
Here I have a physical representation of an Ulam spiral, like what was discussed earlier. This spiral contains almost the first 1,000 integers, and it spirals out counterclockwise from the center at this arrow, which represents the number 1. The direction of the arrow is simply a reminder to the orientation of the spiral. Each of these cubes is placed where a prime number would lay, and you may already notice a few patterns forming, such as a couple diagonals and this long line here to the left of primes. Other than that, though, it might seem like a bit of a random mess. However, if you were to make this spiral larger, you would begin to notice new oddities, like large blank lines along each of the cardinal axes. And if you were to make it even larger than that, you'd notice even more new patterns. It's really quite interesting.
$21.
Stupid.